Today we're going to do a lesson on parts per million and dilution. So we're into lesson 8 of our third unit in chemical quantities. And when you click on this, as usual, you'll have a what do I do set of instructions. You're going to be taken to the summary note here that you will see. And you're going to use that main resource note and you're going to work your way through two sections of the note. So there'll be parts per million and parts per billion. Okay, parts per billion not as common as parts per million, but this is another way of representing concentrations. And this tends to be for concentrations where the solute is very, very small. Okay, so it's very diluted concentrations where there's not a lot of solute, but the fact that there's just even a tiny little bit, it could be a very toxic substance, something that is bad for our nervous system, like lead ion or mercury. And even though there's a very, very small amount dissolved in water, that small amount can still be very deadly or dangerous to people. The other half of the note is to talk about dilutions. And this is when we take a solution and then we add water to it, basically, and we water it down. But the chemical term for that is called dilution. So there are 3 examples I'm going to take you through. The first one is on parts per million, and then down below there are 2 more examples right here on dilution. So I'm going to take you through each of these. So if we go back to the main resource note here, you'll find where lesson 7 begins. And then as we scroll down, you're going to answer some questions on, why are we using parts per million or parts per billion? And then here is the formula for it. So we have seen this formula before, and we have to be aware of the slight differences between parts per million and normal, molar concentration or percent concentration. And it is in the units, okay? So when you're doing parts per million, and it says right here, considered ppm, your mass of solute has to be in milligrams and your volume has to be in liters. If you're dealing with parts per billion, your mass has to be in micrograms. That's the symbol for that. And your volume is in liters. Okay, so just be aware of the differences in units. You may have to convert, it's possible, but that is what we're dealing with initially when we look at these formulas for parts per million and dilution. So for ppm, the concentration is going to be, again, mass of solute in milligrams divided by a volume of solution in liters. If we have parts per billion, which is, again, uncommon, but you might see it, it might pop up in one of the examples. It's the same thing. It's going to be a mass of solute in micrograms, okay, which is just taking this and dividing it by another 1,000, okay, and then dividing by a volume of solution in liters. Now for dilution, dilution is taking a solution that is already made and just adding water to it. So all you're doing there is you're changing the concentration and volume. And so what we do is we use the formula C1V1, or sometimes we'll use I's. I'm going to use I's. So the initial concentration and the initial volume will equal the final concentration and the final volume. Okay, so that is my formula for dilution. So we'll go through an example of parts per million, and then we will go through an example of dilution. Again, you are reading through the main resource note to get the nuts and bolts of what we're covering. I am just simply doing the examples for you here. So here's our first example for parts per million. It says in a 500 ml sample of drinking water, 0.18 milligrams of iron is measured. The safe level, which is the maximum acceptable level of iron in drinking water, is 0.3 parts per million. It says determine whether this water poses a health hazard. Well, we know the volume of the sample, we know the amount of solute, So let's calculate the parts per million and then see how it compares to the acceptable value. So my mass is 0.18 milligrams. This is good. This is the unit that I need. But my volume is 500 milliliters. And I need that to be in liters. So I'm going to divide that by 1,000 milliliters per liter. And I'm going to get a value of 0.500 liters. So we're going to set this up now, and we're going to calculate parts per million. And I'm going to take the mass of my solute in milligrams, and I'm going to divide that by the volume of my solution, that's an S, in liters. And I have both of those units. So again, oftentimes with concentrations, we may have to convert some of our units into grams or milligrams or liters or milliliters, depending on what we need. So we have 0.18 milligrams, and we're dividing by 0.500 liters. And let's see how this compares to what we're supposed to have. So I'm getting a value of 0.36 parts per million. And if I compare that to the maximum acceptable value, it's not a good sample of drinking water. It's too high, okay? So it says determine whether this water poses a health hazard. Yes, it does, because it is higher than the maximum acceptable value. So we're just going to write that down. So yes, it poses a hazard because 0.36 is greater than 0.3 parts per million. Okay, so there's more of that iron in the water sample than should be allowed. So again, this is not really new what we're doing here in terms of the calculation. We've seen some concentration calculations already. It's just the units. The units are very specific for parts per million. And remember, for parts per billion, this milligram value should be in micrograms, which means we would take that and divide it by 1,000 yet again. Let's move on now and let's do two of the dilution calculations. So if you haven't already, stop the note, go back to the summary note and read through the dilution section, and then come back here and follow along with the examples. So it says, calculate the final concentration of a hydrogen peroxide solution if water is added to 150 mils of a 6% volume hydrogen peroxide solution until the total volume is 250 mils. So remember that we have CI, VI equals CF, VF, okay? And the I's stand for initial concentration, initial volume. The F's stand for final. So what they're doing here is they take a hydrogen peroxide solution, they add some water to it, and we want to know what is the final concentration. So what I like to do is off to the side, I like to write down what I know, okay? And again, these are I's, lowercase i's that I'm writing right here. And so we'll just go down the list and we will sub in what we know. So what is my initial concentration? Well, they're asking us to calculate the final concentration. So let's come on over and let's put a question mark there because we know that's what we have to solve for. The initial concentration could be in any unit, folks, okay? It could be in percentage, it could be in parts per million, it could be a molar concentration. They're telling us that this is a 6% volume, okay? And we'll write that down. What's the initial volume? Well, it says, if water is added to 150 mils of 6%, so that's my initial volume of the 6% solution. We want to find out the final concentration, but they add water until the new volume is 250 milliliters. So it's important that you make sure you know what are the initial values of your solution, what are the final values of your solution. So we're going to come on over and we're going to set this up. Now I want to solve for CF, and I've got to take VF out of the equation. So what I'm going to do is I'm going to divide both sides by VF, okay, which allows me to cancel out the final volume on that right side. And then I'm just going to rewrite this, that CF equals C initial times V initial divided by final volume. And I'm going to sub it in. So my initial concentration is 6%. And yeah, you can use that value. My initial volume is 150 mils. So I can use milliliters here as long as my final volume is also in milliliters. Okay, so the key thing here is that units must match. Okay, so if you are dealing with milliliters, you have to have milliliters for both volumes. If it was liters, you could use liters. You just need to have liters in both of the volumes. For concentration, I'm using the 6% solution here, which just means that when I go through and I solve for this, these milliliter units are going to cancel out, and I'm going to have a unit of percent after I do my calculation, which is totally fine. So let's do the math. You're going to follow along with me. We're going to take 6 times 150, and we're going to divide by 250. And I come up with a percent concentration of 3.6%. And this makes sense. Your concentration after, okay, for final should always be lower than your initial because you're adding water to it. You're watering it down. You're diluting the solution. Let's do one more. So here is again another dilution question. It says calculate the final concentration of a 0.400 mole per liter. So notice the unit is different. This is molar concentration of barium chloride. And it says when 125 mils of the solution is diluted with distilled water to a final volume of 500 mils. So my milliliter units are good. They both match. So we can leave it alone. I'm now using molar concentration, but that's perfectly fine. Now when I calculate my final concentration, the unit will be moles per liter. You can use any unit as long as it's the same for your concentrations or the same for your volumes. So let's set this up. We're going to have an initial concentration. We're going to have an initial volume. We're going to have a final concentration. And then we're going to have a final volume. So calculate the final concentration. I don't know what this is. When it says 0.400 mole per liter barium chloride, that's my initial concentration. So 0.400 moles per liter. And we have a starting amount of 125 mils. And then it says they add water to a final volume of 500. So we'll put that in. Oops, put a decimal too soon. 500, there we go, milliliters. So we set up our formula. So CIVI equals CFBF, sorry, not a T. And again, I want to solve for CF. So I got to get rid of VF. I'm going to divide both sides by VF. And then that allows me to isolate the final concentration. So we'll rewrite it. CIVI divided by VF. And then we're going to sub in our values. So I have an initial concentration of 0.4 moles per liter. I have an initial volume of 125 mils. And then I'm dividing by 500 milliliters. So my milliliters will cancel out. That's good. And I'll be left with a concentration unit of moles per liter. So follow along, dig 0.4 times 125. We're going to divide by 500. And I am getting a concentration of 0.1, says the calculator, but I'm going to go to 2 decimal places. So I'll add on a 0, and I get 0.10 moles per liter. And again, you should have a lower concentration because you've added more water. You've diluted it down, and the number of particles that you had are now dispersed in more water, So the concentration of it goes down. Hopefully this is helpful for you. There's a few for you to try. Be in touch if you have any questions.